Okay, hello. My name is Solberg, and this is my presentation for the first virtual conference of structural integrity. My talk is titled "The Effect of Defects from the Manufacturing Process on the Static and Fatigue Behavior of Additively Manufactured Inconel 718." So I'll be speaking about how the loading and geometries are influencing where components or geometries are having failure initiation sites. We'll be using some notched Inconel samples prepared by Additively Manufacturing as examples. Okay, so with fatigue of additively manufactured metals, we typically manufacture something. Here I have the example of powder bed fusion, where powders are fused together by a laser or electron beam and to form a component or a part. So what is typically done is a specimen is built and the specimen is tested, and what we typically see, as we see in C, is that we have a very high surface roughness, there are some defects, and in D we see some anisotropic microstructure, elongated grains. So there are a lot of things going on with these additively manufactured materials, and we need to understand how the features of the manufacturing process are influencing the fatigue behavior. This is some data of common engineering materials produced by additively manufacturing and conventional methods, Roth, and it's Inconel Ti64 316L and 17pH stainless steels. And we see that the general trend is that the as-built additively manufactured specimens are having reduced fatigue strength, while if we see the black dots, those are post-processed, like for example machined or heat treated, these kind of post-processing. So the fatigue behavior is increased to the same level or even higher than the Roth material. Okay, so if we build a notch geometry by additive manufacturing, we're likely to have some higher amount of defects in the downskin regions than in the upskin regions. And if we subject the specimens to fatigue loading, as shown to the right, the defects are likely to be the fatigue initiation site. Okay, so these are some specimens, different specimens, and the fatigue results. So we have a notch geometry, semicircular notch, and 2V notch specimens with different notch radius. And the specimens were built by Inconel 718 powder, and it's solid, no internal structures. Specimens are built vertically, and no post-processing has been done, so these are in the as-built state, and they were subjected to uniaxial fatigue with a loading ratio of R equal to 0. If we analyze the different surfaces, so what we see is that the downskin surfaces are rough, while the upskin surfaces are kind of smooth. And the lower picture here is a polished cross-section from one of the V-notch specimens subjected to 2 million cycles of loading. And what we see is that the fatigue crack does not initiate from the notch root, but from a defect in the downskin region. And these are some typical fractographs from the different specimens. And so we see that the unnotched and the semicircular specimens are having fatigue initiation from one side, while the V-notched specimens in C and D have fatigue initiation from both notches. And in E and F we can see a comparison of the typical defects found in an unnotched specimen in E and in a notched specimen in F. So there are larger defects in the notched specimens due to the orientation of the surface. And we can see some unmelted particles, what we can characterize as lack of fusion. So we did a further analysis of these defects, and we captured all the fracture surfaces and measured the defects as good as we could. I mean, of course, it's a bit difficult when the surfaces are not completely straight, but we measured the defects, and the upper plot is the defect size is reflected in the marker size, and then in the lower right figure the defect size is plotted versus the position within the confidence bands. So we see that for short fatigue life we have large defects, and for long fatigue life we have small defects, and this trend is strongest for the unnotched specimens. And further, we capture the failure initiation sites for the specimens, and what we saw was that unnotched specimens have a large scatter, while the semicircular specimens are failing from the downskin region. So is the V-notch specimens with 1 millimeter radius, while the V-notch specimen with the sharp notch have failure from the center. And then we put this into a diagram using the relative height within the notch and the notch IQT to describe it, and that's shown on the lower right, this diagram. And this is an analytical formulation of the diagram where we described it mathematically. The diagram is separated into 3 sections: unnotched, blunt notch, and sharp notch, where in the unnotched there are not a lot of very downward facing surface close to the minimum cross section, and the scatter is kind of distributed, while for a blunt notch we have a strong effect of the downskin region, while in the sharp notch, the notch is a stronger feature for initiating fatigue than the defects. This is the model fitted with our data. So as we can see, it's a good fit, but of course more experimental data is needed for having a physical model. This is just the first step. And then we also did some static loading. And what we observed, we tested 3 specimens, also including one tensile specimen. And for the notched specimen, of course, we had the notch strengthening effect and the lower elongation, while for the tensile specimen we didn't have the notch strengthening effect and longer elongation. And then we tested going from static loading to fatigue loading in order to see the trend. And so we see that somewhere within the low cycle fatigue range, we have a transition from notch strengthening to notch weakening. We can also see the difference in the fracture surfaces, where in A and B is the fracture surface and C and D is the front view of the fracture surfaces. And we see that in the static loading, the fracture surface is ranging across the notch bisector line, while for fatigue it's not ranging across. Its failure is just occurring from the downskin region. So this indicates that fatigue is controlled by the small defects in fatigue loading, while in static loading those are not as dominant. However, it seems like the fracture surface is controlled by the fact that the defects are present in the downskin region, as the surface is ranging across or higher towards the downskin region. And in both cases we have defects in the fracture surface. And here we captured, as a kind of extension of the previous diagram, we plotted it with maximum stress. So for a low maximum stress, this would be corresponding to high cycle fatigue, while a high maximum stress is corresponding to somewhere close to static loading. And what we see is, of course, for the unnotched, we have the large scatter and fatigue, while the fracture surfaces are ranging across the minimum cross-section for static loading. And the same is seen in the notched. We have failure initiating from the defects in fatigue and then ranging across the minimum cross-section in static loading. Okay, so conclusions. Notched weakening is observed in fatigue loading, and the strengthening is observed in static loading. Fatigue cracks does not initiate from the designed notch route under fatigue loading, but from defects. And the defects and higher surface roughness are present in the downskin region, causing this. And the failure locations are focused towards the minimum cross-section in static loading. However, the defects are still influencing the failure location at static loading. Okay, so that's all I had. Thank you for listening, and hopefully we will have some kind of discussion in the comment section. Bye.